coming for share with us this webinar. I'm glad to introduce to you our president, Mr. Michael Greiner, that he managed this presentation to all of you. Okay, Mike.
Okay, thank you, Renan. I want to also welcome everybody to the webinar. Renan, if you would monitor my mic and just let me know that it's not too scratchy. Sometimes I get very passionate about things and my mic starts to squeak. Today we're going to talk about the F500 Encapsulator Agent and what we call concentrate control supply systems. So our motto is to encapsulate the world. That's our mission, to encapsulate the world, to make it a safer place through leadership in fire prevention, protection, suppression by providing an eco-friendly, innovative technology. And what we're talking about today is more than just F500 Encapsulator Agent. We're actually talking about Encapsulator Technology, which is a whole new category of agents. We're located in Atlanta. That's our main headquarters. Our specialty is fluorine-free encapsulator technology. We do engineered systems. In addition, we have emergency response teams. We do training and consulting. Been in business since 1997, and we are worldwide. In fact, I saw a couple of our folks logged in here from South Africa and some from over in Singapore and in the Far East. We choose to be stewards of the industry, which means we're Nfpa members. I myself sit on 3 separate Nfpa technical committees. Other members of HCT organization also sit on different Nfpa technical committees as we try to bring this encapsulator technology to a higher level within the Nfpa standards. Recently, we're contributors to IFSTA, International Fire and Safety Training for Firefighters, Society of Fire Protection Engineer on staff, multiple engineers. And did I mention we're an ISO 9000 registered quality management system? I think the importance of that is that we do a lot of demonstrations of the product and you see this amazing product performance. And being that we're an ISO 9000 company, it means we make reproducible results every time. So when a customer sees the performance of what's in the pail that he's looking at, he can be assured when he makes a purchase, he gets that same high level of performance out of what he receives. Today's technology creates new hazards. You know, we haven't stood still. I know UL has a very interesting video that's showing in the 1960s, it would take a little over 30 minutes to get to a flashover based on the furnishings that were in a living room in the 60s. Now we pop forward to 2020 and we walk into the same living room and we see all these new materials there and it only takes 4 minutes. So that means when the fire department arrives at a structure fire, the big question they should be asking themselves, are we bringing a knife to a gunfight? Because the hazards that we're facing today are much higher. Lithium-ion battery fires. I know a lot of people think about Tesla and Chevy Volt and cars, but lithium-ion batteries around us all over the place. iPads, cell phones, computers, you name it. Even the extraction equipment the firefighters are using to pull people out of cars are battery operated. And so we have that three-dimensional fires in all kinds of industries. Class D, you know, magnesium, titanium. As the world says, let's recycle, let's get better at reusing our stuff because planet Earth only has so much to do. We start to see a lot of hazards that are generated out of those business. Currently, when you go back to the Nfpa standards and UL listing, the only criteria that exists for listing on a metal is for a fire extinguisher. So if you're a fire department or you're a big metals recycling, you got this pile of scrap metal to protect. What are you going to do? Buy 75,000 fire extinguishers? So being stewards of the industry, working in the codes, and the fact that we have an agent, the encapsulator agent that works in this, we're updating the codes and subsequent protocols to bring these type of solutions to the market. Today, we're going to talk a little bit about the concentrate control supply systems. We call it CCS systems. So this is the proportioning equipment that's needed to proportion the agent into fixed sprinkler systems. Our agenda today is going to include overview of encapsulator technologies and features of the encapsulator technology, applications of encapsulator agent, some slides on the systems themselves and the components of the systems, and then some actual application examples. So today we want to understand the difference between not just foam and encapsulator agents, but what's the difference between water, wetting agents, foams, and encapsulator agents. Well, we're going to explain the characteristics of the encapsulator agent, discuss applications, and then identify the industries where the EA can be used. So,
the old and familiar representation of a fire triangle has been replaced with a fire tetrahedron because we now know and recognize a fourth element crucial to combustion, a chemical chain reaction. The four sides of a
Can't hear it, Mike.
okay, can't hear it?
Yeah, the volume's really, really low.
I'm afraid if I turn up the speakers. Okay,
fuel,
better?
oxidizing agent, and the chemical chain reaction.
Yes, that's
Mike.
better.
Or more of these components are absent, a fire cannot occur. When all four components are present, heat, fuel, oxidizing agent, and the chemical chain reaction, fire will occur. There are four options for extinguishment: cut off oxygen, cut off fuel supply, thermal insulation of the fuel, and interruption of the chemical chain reaction. When one or more of the components are removed, the flame goes out.
So we're going to talk a little about encapsulator agent and how it interacts with the fire tetrahedron. We developed this technology back in 1996. We have patented the technology. In fact, we have about 6 or 7 additional picket patents around the original process patent. Over the years, we first developed the product as a flammable liquid spill control, sold it to a bunch of the fire departments around the Atlanta area, and then they started calling us questions about fire. They were like, oh, we put this fire out, and boy, this black smoke turned to white, and we've never seen that before, and holy cow, the heat, it just disappears, and there's no steam, and what's causing that? And really at that time, our question was like, well, wait, that's a spill control agent. What are you doing using it on fire? They go, oh, it's been working great. So we got out and got together with the customers in the community and started to learn more about the product, and hence we've parlayed the encapsulator technology into multiple applications, including the flammable liquid spill control. I think it's important to start out, when we first start out in 1997, you have a new technology, it's patented, you're bringing it to the market. At that time, there were 2 standards. There was the Nfpa 11 standard, which was low, medium, high expansion foam. Well, the F500 encapsulator agent doesn't create bubbles, and it's not really, our mechanics aren't based on forming bubbles. So we had to list into a wetting agent in the time being so we could work with the NFPA Standards Council to create a new category of agent. I had put forth that we would make it NFPA 19 encapsulator agents. At the time, there was a whole bunch of gel manufacturers who have long-term retardant gels, and they decided they were going to try to jump into this committee. So it turned out that the standard became NFPA 18A water additives for fire control and vapor mitigation, and NFPA 18A section 7.7 provides for what we now call the spherical micelle stability test. And that procedure covers how to determine, does an agent actually create stable spherical micelles that are capable, of encapsulating flammable liquids and maintaining that encapsulation in the presence of high heat. So at this point, some people might be going, well, what are we exactly talking about? So the basics of the encapsulator agent, the basic building block is something called a spherical micelles. And these micelles, yes?
Sorry, be careful because we start to listen some scratchy noise, like static.
So these micelles are capable of encapsulating both carbon molecules and class B materials, both polar and non-polar, as well as hydrocarbon liquids and vapors. So we can encapsulate whether the fuel is in a liquid state or if it's in a vapor state. And that really is going to present a lot of new advancements in fire technology and fire prevention. So basically an encapsulator agent is separating the fuel from the oxygen. We're just doing it on the chemical molecular level as opposed to foam that's doing it on a mechanical macro level. And we'll talk a little bit more about that as we go. So let's take a look at what is a micelle and what does the F500EA droplet look like.
Encapsulator Technology.
Can you hear this?
The next generation of fire and hazard mitigation.
Can you see
First,
it?
we start with a simplified version of a single encapsulator agent. Encapsulator Technology, consisting of a hydrophilic polar head which loves water, dissolves in water.
All right, well, I got two of them going now.
Non-polar tail, which fears water and will do anything to get away from water. Once the EA molecules enter the water, they instantaneously and automatically orient with non-polar tails inward and the polar heads out. Once the EA molecules enter the micelles, they instantaneously and automatically orient with non-polar tails inward and the polar heads exit the millions of spherical micelles. Micelles nearest to the surface of each droplet automatically the nozzles from the non-polar tails orient outside the droplet with polar heads on the surface.
Sorry. This is very important, and I got two versions of it running.
Encapsulator Technology. The next generation of fire and hazard mitigation. First, we start with a simplified version of a single encapsulator agent molecule, consisting of a hydrophilic polar head which loves water, dissolves in water, and a hydrophobic non-polar tail which fears water and will do anything to get away from water. Once the EA molecules enter the water, they instantaneously and automatically orient with non-polar tails inward and the polar heads outward, forming millions of spherical micelles. Encapsulator Technology.
Oh my goodness.
The next generation of fire and hazard mitigation. First, we start with a simplified version of a single encapsulator agent molecule, consisting of a hydrophilic polar head which loves water, dissolves in water, and a hydrophobic non-polar tail which fears water and will do anything to get away from water. Once the EA molecules enter the water, they instantaneously and automatically orient with Non-polar tails inward and the polar heads outward, forming millions of spherical micelles. Micelles travel towards and exit the nozzles, forming EA droplets. Micelles nearest to the surface of each droplet automatically break apart. The non-polar tails orient outside the droplet, polar heads on the surface, forming an EA skin on the surface of every droplet. In addition to the EA skin, there are millions of molecular spherical micelles within each droplet.
I apologize for that. That went through this about 10 different times. So what we're looking at here is we're seeing a droplet, and on the skin of the droplet is I like to think of this like an orange. So on the skin, which would be the peel of the orange, is F500 molecules, and we have the non-polar tails are sticking out because they hate the water. The polar heads are dissolved right in the surface of the water. So we're formed a skin on every droplet. That's very important based on heat reduction, and is the reason we're very effective or can actually be applied to class D is because of this F500 skin. But then as we do the cutaway, we look inside and we see millions of spherical micelles inside each droplet. Here they're blown up just so you can see what they look like. But if we were to put this into size, how big are these micelles? Okay, if we blow this droplet up to be the size of Earth, then the micelles that are inside that droplet are actually the size of peas, the size of rice, the size of a BB. They are very small compared to the size of the droplet. But there are hundreds of millions of spherical micelles inside each droplet. Those micelles perform three major functions. The first one is the encapsulation of carbon and hydrocarbon polar fuels. So encapsulation is one of the functions. Second one is the rapid cooling effect that is achieved by the spherical micelle. And the third one is the interruption of free radicals, and which leads to the reductions of toxins. And so we're going to address those. First, the rapid heat reduction. Somebody once told me you can't change physics. A gram of water can only absorb so much heat. And my response was, you're 100% correct. We're not changing physics. We're changing the material. We're changing the substance on the surface of the droplet, and we're changing it from an H2O molecule to an F500 molecule. In addition, inside, we still have all these spherical micelles. So what's happening is an H2O molecule doesn't transfer heat very well, where the F500 molecule transfers heat very well. So we are now taking the heat and we're pulling that inside the droplet. We're taking it around the surface of each micelle. And again, there's millions of micelles in each droplet. And then we're slowly transferring it into the heat. So I like to think of the F500 as being like the Ferrari. We're transferring heat very fast like a Ferrari through the F500 and then transferring it into the droplet. Think of that like a bicycle very slowly. So when you compare the plain water versus the F500, what we see is, okay, we come out of a nozzle, and it doesn't matter if this is a sprinkler head, an open head deluge, an IFI rotating nozzle, an HETV nozzle, or even a hand line, we come out at room temperature. And in this case, we're using 70 degrees, and that water droplet's traveling towards the fire and towards the heat. What happens, like an onion, the outer surface of that droplet heats up and converts to steam. So you off gas that into steam, but you see here, 95% of that droplet hits the back wall, comes down on the floor, and basically we've increased the temperature from 70 degrees to 72, with some of it coming off as steam. So that's steam conversion, or some places of the world call it evaporation. And the F500 actually changes that mechanism. Instead of steam conversion, we have thermal conveyance. So what we're doing is using the thermal conductivity properties of the F500, and we're pulling the temperature into the droplet. So here, if we come out at 70 degrees, the droplet becomes 80, 90, 100, because the temperature is going in the droplet and being transferred around the micelle and into the water molecules inside. So we get a rapid heat reduction, a very rapid knockdown of the fire, but one of the biggest benefits is the no steam creation. And I know I've been called BS on this multiple times until people have actually seen it. So they've actually been in the flashover simulator or inside a warehouse or an enclosed area. They put F500 in, the temperature drops immediately from 1400 degrees down to maybe 110 degrees, and there's no steam, and they're like, wow, where did the heat go? So something totally unique. And remember, heat's one of the legs of the fire tetrahedron. And actually, it's one of the forgotten legs of the fire tetrahedron. You get rid of the heat, you get rid of the fire. So the heat reduction capability of F500 is 6 to 10 times greater than plain water, depending on a droplet size, and somewhere in the neighborhood of 10 to 20 times greater than foam. And we'll address that later on in the presentation. The F500 encapsulates fuels, rendering them non-flammable, non-ignitable, and non-explosive. So there's a test in Nfpa 18A, section 77, called Spherical Micelle Stability Test. So while you have UL162 is a foam qualification test, now we have Nfpa 18A section 77 as an Encapsulator Technology qualification test. So we'll talk about that as we move forward. We have a specific encapsulation ratio that is used to accomplish the encapsulation, which takes 1 part of F500 encapsulator agent, 8 parts fuel, and 40 parts minimum of water. I'll get back to the minimum. And then kinetic energy, some sort of agitation, usually provided by just the nozzle stream or the sprinkler stream going on to the fire. If we look at this ratio here of 1 part of F500 to 40 parts of water, we end up with a 1 over 40 is 2.5%. So technically, we can encapsulate with the 2.5% solution, but since most existing fire equipment is 3%, we just dial our Class B up to a 3% mixture. Over here, if we look at this ratio here of 1 to 5, 8 parts of fuel to 40 parts water, that breaks down to 1 to 5. So what does this mean? How we utilize this is we say, okay, we have a 20 liter, for those international, a 20 liter spill. It could be a 20 gallon spill on the roadway. If we take 20 and multiply it times 5, we get 100 liters. So if we take and put down 100 liters of a 3% solution of F500, we have then put down 3 liters of F500. And 3 times 8 means we could have encapsulated 24 liters of fuel, but we only had 20 on the ground. So this is a quick and easy way for fire departments petrochemical companies, refineries, any industrial facility that deals with flammable liquids to look at a fuel spill and go, oh, I have a 10-gallon spill, 10 times 5 is 50. Let me put down 50 gallons of a 3% solution of encapsulator agent to encapsulate it. You would use an LEL meter, gas detection meter, and show that the vapor off-gassing is 0 because we've totally encapsulated it. Now, you can't do that with water. If you sprayed water down, the fuel is lighter than water. It's going to float on the top, so we all know that. You could put foam down, but a foam blanket will dissipate. You'll have to apply foam a second time or even a third time. And you can't do it with a wetting agent because a wetting agent doesn't encapsulate. So this encapsulation is a unique feature to our product and this category of agent known as encapsulator agent. Here I'm going to show you the spherical Micelle stability test.
And we're demonstrating the NFPA.
I'm going to turn this off. So this is NFPA 18A section 7.7. If we look in the current standard, we see it says emulsifier test, but that's absolutely incorrect because an emulsifier is like oil and vinegar. Mayonnaise is an emulsification. So it's a mixture of two different substances in a colloidal suspension. And what we're dealing here is 3 different substances. First, the fuel. So we put in a gallon of fuel. Now we're mixing in a pint of the agent. If we were doing this metric, we would be putting in 4 liters of fuel and 500 milliliters of agent. So that's that 1:8 ratio. Now we're taking a calibrated nozzle. So if we're doing this in the SI units, this is a 5-gallon per minute calibrated nozzle, and we're going to apply for 1 minute. If we're doing the metric system, this is a 20-liter per minute nozzle, and we're going to do 1 minute. So I'm going to try to speed ahead here just a little bit. So we've taken 1 minute, we've mixed in the water. Now the test says wait for 1 minute, and then we're going to put a torch to the top of this surface of the pan here, to the complete surface. And we cannot have ignition. If we look at the pan, we don't see any foam bubbles. If this was plain water, the fuel would float up on the top and it would light instantaneously. If this were a wetting agent, again, the fuel would float up on the top and it would light instantaneously. If we were to put down a foam blanket here on this test, you would see lots of foam bubbles. When you lit the torch here, you would see candling of the vapors that are in the bubbles, but you would not get a free burn. We've done this with our Class B foams and some competitive Class D foams. And what happens is some vapors get trapped in the bubbles. So as soon as you hit it, you get some candling of the bubbles. But again, that's not qualification as not passing. So the foam will pass the 1 minute test. But this test also has a burn back resistance test 2 hours later. Hope I didn't miss that mark. So we're going to let it sit, and then we come back 2 hours later and apply the torch. Well, again, the plain water and wetting agent failed the 1 minute. At this point, the foam blanket is totally dissipated, and this would light off like a Roman candle. And here you can see the encapsulator agent. I'm taking my torch and throwing extra flame in there, and you can see it's still not lighting. So what this has shown is that this particular agent that's being tested can create spherical micelles that are capable of encapsulating the fuel, and they're stable micelles for a long period of time and stable in the presence of high heat. So those are the features here. So on one hand, the foam would not be able to pass this test because foam is not an encapsulator agent. At the same token, the F500 will not pass UL 162 because that is a foam qualification test, and our product is not a foam. So we're really differentiating that we have two totally different categories of products. The third feature is this interruption of free radicals. And as free radicals come together, sometimes it's referred to as combining or coalescence. That's what causes the toxic soot and smoke. So think of free radicals as they join together, they're forming the toxic soot and smoke. So we had a Clemson University, their environmental division ran some tests. So they set up this plenum over here, have a light source, a light on one side, and a light receiving source on the other side of the chimney. You can see as you're burning, smoke is coming up through the chimney. They spray plain water through here, and they were measuring the amount of light that came through and was received on the other side. Also had an air sampler that was sampling the air that was coming out above the chimney here so that we could analyze the toxicity from the air emissions, as well as we evaluated the soot buildup. So you can see here with just plain water passing through the smoke flume, we end up with a lot of soot buildup on the plenum. With the F500 encapsulator agent, that was greatly reduced. The smoke was reduced. So here were the results. In this test, we saw a smoke reduction that caused a 68% increase in visibility. So 68% more light came across. Now that's going to range. Toluene is pretty dirty. Diesel fuel is pretty dirty. Certainly rubber tires are very dirty. So that number may actually go up for the F500. But if you took something like, say, a heptane that burns pretty light and doesn't generate a lot of smoke, those numbers would be a little bit less. The smoke accumulation on the plenum was reduced by 97%, which is quite amazing. That's a function of two things. The first one being we're interrupting the free radical to minimize the soot and smoke production. And the second one, we're actually encapsulating the unburnt carbon or hydrocarbon materials so that they can't form in the atmosphere. And then soot and smoke toxicity. So we actually looked at the toxicity difference between the plain water and the toluene, and we saw a 98.6% reduction in the toxicity, which is quite big in today's day when firefighters, the incidence in firefighters, health and safety people, the incidence of cancer is 30% higher than any occupation. Anything we can do to improve the health and safety in an industrial environment would be excellent. You know, we have a global crisis going on right now, PFOS, PFOA, starting to come to a head. There's all you have to do is Google and you'll see lawsuit after lawsuit, all kinds of things. And yet we have a fluorine-free technology because fluorine is what foam used to generate bubbles. We're starting to see some fluorine-free foams. I would say at this point, every foam on the market is PFOA or PFOS free, not PFAS free. In addition, the F500 extinguishes A and B. It works on D, K, and lithium-ion batteries with no fluorinated ingredients. So it's both effective and healthy. Anytime we have, a fire protection consideration, I'm just going to break down into three categories. We might consider water. we might consider a foam, either a class A or B foam. We might consider an encapsulator agent. So there's different options that are available to protect items. And what we have to do is be able to look at the features and the benefits of each one of those different technologies to see what one might best suit that particular application. For example, water, we know it's pretty ineffective at reducing heat, and it converts H2O molecules to steam. So is that what we want to have in our environment, to subject people to, let's say a rubber tire warehouse sprinkler system? Foams, we know the foams have been around a long time, good quality product, good technology. They blanket and separate the fuels from the oxygen to smother the fire. To us, a counterproductive thing of the foam is we're putting down a blanket. And, I know that when I'm lying in bed at night and I'm cold, what do? I pull up a blanket because it insulates me and traps in the heat. And that's exactly what we see with the foam. So you put a blanket down, it's going to trap in that heat. That's why in the UL 162 test, which is your foam qualification test, not only do you put out the fire, but you're subjected to a burn back resistance test because you haven't lowered the heat below the auto ignition temperature of the fuel. So you have to maintain a good separation to keep vapors from coming up, or they'll reignite from the heat still in the steel pan. Also, we see that it could be limited to two-dimensional class B. In fact, when we go to the Nfpa standard, it says the 11 standard specifically states foam is not suitable for three-dimensional class B flowing fuel fires. Or if we look at an encapsulator agent, we got rapid and permanent heat reduction.
Mike, sorry.
Yes.
Mike, sorry.
Too loud.
But yes, too loud. I know that this part you start to be with more passion. This is why
no problem.
Yeah.
So,
Okay.
so we have rapid and permanent heat reduction, 6 to 10 times greater than plain water. We encapsulate the fuels, so we have permanent encapsulation of the fuels. So we're separating the fuel from the oxygen. We're interrupting the free radicals, which helps to provide for the quick knockdown. It works on two-dimensional and three-dimensional class B. So here again, we're just kind of comparing the three technologies. I think sometimes this makes a lot of sense when people go, oh, well, wait, yours is a 5-gallon pail and it's liquid and it's in a bucket. And they want to call F500 a foam. So we're always saying, no, it's F500 EA, F500 encapsulator agent. We don't promote it as a foam. It's not a foam. So over here, if you look at a wetting agent, they reduce surface tension that helps spread and penetrate. But when you look at the heat reduction, you have the same mechanism as water. It's a steam conversion. So because you have a wetting agent with reduced surface tension, you'll get some smaller droplets automatically as a function of the surface tension reduction, which means you have a little more surface area, which means you'll end up getting more steam conversion. You'll have a moderately better heat reduction in plain water. The downside is you'll create much more superheated steam. It's something that the firefighters and most health safety engineers don't like is additional steam. With a foam technology, you get surface tension reduction. In the foam standard, it's actually referred to as spreading coefficient, and it aids in spreading the blanket. One of the differences here is you're forming a blanket. So the basic building block, as we see here, of a foam is a thin wall bubble structure or a film, but you have a bubble structure, and we're putting all these bubbles together to form a blanket to separate the fuel from the oxygen and mechanically smother the fire. Again, I've mentioned that we trap in the heat, it's counterproductive, and it requires that we maintain that separation until we can allow that heat to slowly dissipate. Encapsulator agents reduce surface tension, similar to a foam that what aids in spreading the micelle, spherical micelles, the micelle encapsulator agent. We're encapsulating fuel and vapors inside the spherical micelle, separating the fuel from the oxygen on a chemical molecular level. We change the heat reduction mechanism of the droplet to account for 10 to 20 times faster heat reduction and interrupting the free radicals. So here you're working on 2 legs of the fire tetrahedron. Here you're working on 4 legs of the fire tetrahedron at the same time. These are the applications that we've done for fixed systems. Class A, we've done warehouse, flammable, we've done rack storage for rubber tires. We've done a project with Boeing where they had composite materials where they realized, ooh, plain water is not going to be able to put out these fiber composite materials. So we did some testing with them and with their insurance company because there's currently no testing criteria for Class A fires for fixed systems. So we had to create our own testing protocols with Boeing, and they showed that the encapsulator agent could put out this composite material and would put it out at half the density at which the plain water would only control the fire. We break Class B into 2 sections, into the 2-dimensional fires, like fuel spill fires and fuel in depth fires. And we have systems in place for those. But we also have 3D Class B fires. What are those? Those are like your spray fires, like maybe a distillation column, transformer fires, lube oil, under turbine lube oil, pump seal fires, pipeline fires where you might have a broken seal at a joint or some sort and fuel is coming out under pressure. Well, those are not applications that you can blanket with the foam blanket. And as we look through the Nfpa standards, we see that the way those are getting addressed are 3 options: water, more water, and oh my God, even more water. So those are the 3 options. And now the F500 encapsulator agent actually provides a very good option for 3-dimensional Class B fires. Class D, you will look at me kind of strange because, oh, you can never put a water onto a Class D fire because of the fireworks. We actually have several fixed systems in place, in operation, in North America, approved by the authority, having jurisdiction where they're actually sprinkling large piles of Class D magnesium and titanium. So again, something very unique prior to encapsulator agents has never been done. Class K, we do not have any fixed systems, just that we know we can work on Class K materials, and we are on the back burner looking at creating a kitchen system, but not our highest priority. Lithium-ion batteries. We currently have anywhere from 18 to 25 fixed systems in operation protecting lithium-ion battery hazards for Tesla, General Motors, Element, Jaguar, Ford. I know I'm missing a few, BMW, Daimler, Chrysler, and some other places. So the scope of the applications for the encapsulator agent really can open up the market. One other thing that I don't show on here is that let's take a pump. seal that's at a refinery, and this seal starts to leak, so fuel is coming out, and now we have all the vapors coming off that fuel that's coming out. Eventually, those vapors are going to go and find a nice hot steam pipe, cause a massive explosion. Well, with an encapsulator technology, with this spherical Micelle, all of the pieces of the puzzle are in place to be able to have a vapor encapsulation explosion prevention system. We would be able to put detection equipment in, detect that vapor release, automatically send the signal to the control panel, have the operators isolate that valve, shut that area down to shut off the flow of fuel while we dispense an encapsulator agent through the vapor cloud, removing the hazard, preventing the explosion, preventing the ensuing fireball, preventing damage and possibly injury and loss of life to people. This is just a quick video showing some of the capabilities. Turn this off and I'll walk us through this. So one agent, multiple applications. Here, Class A. Two things there. The first thing was that's just a small 20-gallon per minute nozzle. Total extinguishment here in less than 15 seconds, so it was 5 gallons of product. And I don't know if you noticed black smoke turn into white. And here we have a vapor. This vapor would be like being in a warm, moist shower. That is not steam. That's not at 212 degrees. It's not at 100 degrees C. It's like being in a warm, moist shower. It's not even like being in a sauna bath. If you go into a sauna, that's way hotter than this vapor coming off here. Again, I want you to see the tires are still on fire, but all the black smoke is dissipated. That's because the agent is interrupting the free radicals, preventing them from coming together to form more soot and smoke. So in addition to the fast knockdown, I stopped it a little too late. You can still see the fire, but no smoke. This again is a 20-gallon per minute nozzle. If we look over in this part of the video, we see they were just checking to see if the agent was actually flowing through the nozzle, so they were checking it. That little bit of checking if the agent was flowing is way more than the runoff from putting out the fire. So this is a flat spill. This is the last one was fuel in depth. This is polar solvent flat spill. These are three-dimensional flowing fuel fires. Here we're encapsulating the fuel inside the chemical cocoon, separating the fuel from the oxygen so that the flame front heat doesn't impact it. This is LNG gas, lithium-ion battery. This is some testing that we did in the Netherlands. And this was actually testing conducted in conjunction with Johnson Controls and Johnson Controls over in Europe, who we've teamed up with on Encapsulator Agent for lithium-ion battery applications in Europe. That's a Class D. This is just showing a quick extinguishment of a transformer. There you see they start to apply the encapsulator agent. It's knocked down. Fixed systems. When we talk about putting it into sprinkler systems, we have two different types of concentrate control supply systems. One is a bladder tank system and one is water-driven proportioner system. So this is your typical layout of a bladder tank system. This just shows a one riser configuration. You can have a multiple riser configuration. Could be 2, 3, 4, 5 risers. I think we've done as many as 10 risers in one system. But here's a backflow check valve or an OS and Y valve. And then this is a deluge valve. So basically how this system is going to operate is the hazard is the detection on the hazard could be any number of things. Could be a CO monitor, could be thermal imaging, could be protecto wire, linear heat detection. So there's multiple ways that you could detect that you have a fire. Once the fire is detected, sends a signal to the fire panel, kicks off the alarms, whatever notification goes into place, and then comes back and opens up the deluge valve to allow the water to start to flow. As the water starts to flow, goes into the outside of the bladder tank. So this is a steel tank. Inside is a bladder. Inside the bladder is the 100% F500 EA concentrate. So as the water is going up, it's coming through a ratio controller, which is your proportioning device. The water's coming here. It's squeezing that rubber bladder. I like to think of it like squeezing a tube of toothpaste, and the toothpaste is coming out the top. Well, that's what's happening here. The water pressure is squeezing the toothpaste. It's coming out here, and the concentrate is flowing and proportioning right here. And here you have an F500 solution going to the nozzle system, the sprinkler systems, to protect the hazard. What keeps this agent from automatically discharging from the tank is right here is a hydraulic actuated control valve, and we'll have a piece of tubing that comes down to the deluge valve. So once the deluge valve opens, it sends a water up here to hydraulically open this valve to allow the agent to flow. The agent would be proportioned in at a most, we typically just use 1% for a class A materials, like the composite material in Brazil was 1%, rubber tires here in North America, 1%. And then for flammable liquids, we would use a 3%. For lithium ion battery, 3%. And for class D is 3%. So the ratio controllers that we have range from 2-inch up through 8-inch with orifice sizes for either a 1% or a 3%. So this is showing better the different systems here. So you have your deluge valve that opens up, and here's the bladder tank itself. This is the sight gauge on the bladder tank and a fill line. When we supply these systems, we'll supply the bladder tank with compatible bladders, which is very important because I know when you deal with a foam system, you deal with a 100% completely UL listed system. So the specific bladder tank is UL listed with the specific foam. The ratio controllers are tested and verified and confirmed with that particular foam, so on and so forth. So since the current encapsulator technology listing criteria for this equipment doesn't exist, we have pulled the applicable parts of UL 162 and run the test. Early on, the very first system that was ever installed used an Ansel bladder tank, but the customer insisted to use F500 Encapsulator Agent. It was for a hydraulic pit press. It was a 3-dimensional Class B fire. When it caught on fire, they couldn't put it out with water. They couldn't put it out with foam. And the fire department showed up with F500 EA and instantly put the fire out. So when they put the fixed system in, they demanded F500 EA. We weren't even in the business. That was the project that got us in the business. The reason it got us in the business was because Ansel sold the tank. The contractor installed the tank, put the agent inside the tank, and we got a call 6 months later that the agent has eaten up the glue seams of the bladder tank. What are you going to do about it? So the bottom line is we have an encapsulator agent. Inside those bladders are glued seams. There's 3 components, a top piece, a bottom nozzle piece, and the center piece, and those are all glued together. And our agent encapsulates hydrocarbons. So over a short period of time, about 6 months to a year, it encapsulated the glue and the bladder came apart. So it was at that point we said, okay, we need to get into our own bladder system with our own bladder that's been tested, that's compatible with our agent. So when we supply the system, what we supply is our bladder tank and bladder. We supply this hydraulic actuated ball valve, this yellow thing. We provide the ratio controllers with the proper sized orifice plates. We come on site. We provide filling of the tank, commissioning, startup, and proportioning testing to verify that we're actually proportioning at the designed proportioning rate, not less than design and no more than what's required by Nfpa 25. So our package is pretty comprehensive package, gets sold to the contractor, installed by the contractor, and then we come out and do the commissioning and startup service. Different systems, these are some Class A systems that have been put in place. This was for the protection of Class A combustible dust, in particular Powder River Basin coal. These are smaller systems because the sprinkler density in these conveyors or a dust collector or silos is usually 0.15 to 0.2 gallons per minute per square foot. The proportioning rate would be a 1%, and the duration is usually about a 10 to 15 minute duration of agent, usually with a 10 or 15 minute reserve. Again, there's nothing in the code that calling for this, and why they're being installed is because the plain water systems won't work and are actually a detractor and can cause an explosion. So they're putting this agent in to stop that. So usually our recommendation would be 15 minutes with 15 minutes of reserve. So here's a L&S King up in Minnesota. This is used for a coal silo headspace for a fire washdown dust suppression system. These were used in the crusher house, here used in dust collectors. The second type of system that we use is called a water-driven proportioner. Walk this through here. Our branding on that is called HET Diamond Doser. So what you have is a main water motor. So your water is going to pass through this water motor. I guess I'll wait for the slide to catch up. This is just showing the different components going together. These water-driven proportioning systems are a little bit like a fuel injection in your automobile. So here we're connecting up the main line. This can feed to monitors. This could feed to standpipes, hand lines. This could feed to a sprinkler system. This could feed to a VEEP system, a vapor encapsulation explosion prevention system. So as the water is flowing through the water motor, it's turning the motor. As the water goes faster, the motor goes faster. As the water goes slower, the motor goes slower. Then you have an agent holding tank. That can usually be a plastic atmospheric tank. Open the valve, allow agent to flow through. So as the water turns the motor, it's turning these pistons, which is actually injecting the agent into the water. Most systems are standard, either a 1% or a 3% systems. Some of them you can get a speed adjuster here to adjust from a 1 to a 3. Those may be used on mounted on a fire truck, for example. Let's say every system we've put in so far is either a 1% or a 3% fixed system based on the hazard. So here it's just showing a flush. After you're done, you just flush out. And then when it comes time to fill the tank, usually it's just pop the lid off the tank, pump more agent in, and you're ready to go. As opposed to bladder tanks, once you've discharged a bladder tank, it requires a lot of work to refill those tanks. I was having a discussion today with a customer, and he was trying to ask me what's the difference between the bladder tanks and the diamond doser system. So let me explain that here. If once you open up your deluge valve on a bladder tank system and the concentrate, the hydraulic actuated control valve is open, you are going to start squeezing that bladder, and the agent will come out into the ratio controller, and it will continue to come out until somebody either closes the hydraulic actuated control valve or shuts off the water feed line going into the bladder tank. So you may have 30 minutes of supply of agent, but put the fire out in 3 minutes. Unless somebody physically goes and isolates the tank, you will discharge all 30 minutes of agent. Even if you stop the flow of water, if you don't isolate the tank, the agent will just come out and fill the feed line going up to the hazards. Where with the water-driven proportioner, when you stop the water, it stops flowing through the water motor, so the piston stops, so agent flow stops. So this is just one of the projects here. You can see down here the water is going to flow. I can't tell from here which direction, but one direction or the other. I believe water's coming in from this direction, going through the water-driven proportioner, and then it's going up to whatever the hazard is it's protecting. In the meantime, this one just used a 275 gallons, happened to be the requirement. So we can just use a standard 275 gallon IBC tote or 1,000-liter tote. We raised the tote and put it on this spill containment area. We often do that only to isolate it away from any forklift traffic you might have. If somebody were to poke a hole in the tote, all the agent would still be captured here. You wouldn't lose the agent. You could just replace the tote, pump the agent back into the tote, and not lose 1,000 liters of agent. But as this system runs, the agent comes through the pipe and gets proportioned right here. So what you end up with, this is plain water, this is 100% concentrate, and then going up to this would be, in this case, a 1% solution. And in this application, this is feeding a sprinkler. It's a hybrid washdown fire protection system in the silo, as well as feeding a standpipe up in the tripper room to accomplish some washdown. Three-dimensional Class B fire protection, multiple applications for this. We're just going to highlight a couple. The under turbine lube oil spray system. Again, we look here and we go, okay, these are our considerations. We can use water. When we look at the NFPA standards, it specifies application densities. The approach is to control the fire, not to extinguish the fire. We certainly know the plain water is not a good fire extinguishment agent for Class B. If it was, we never would have invented foam, and further wouldn't have invented encapsulator technology. So it's not effective. When we look at foams, forms a blanket. It's not conducive to these three-dimensional flowing spray fires. And here, when we pull up the NFPA standard, this is the NFPA 11 standard. I hope I haven't messed myself up in the presentation. Here I'm in the Appendix A, A11, and well, I can't blow that up. Hopefully we can see this. It says foam is not suitable for three-dimensional flowing liquid fuel fires or for gas fires. We see foam used in a lot of applications, like flammable liquid rack storage. That's a three-dimensional type fire. We see high expansion foam systems used a lot because, you know, it's pretty well understood, geez, I'm not going to be able to blanket this unless I have a total flooding high expansion system. So sometimes when we see those systems used for these three-dimensional Class B type fires like a transformer, I often shake my head because the base standard for foam says it's really not suitable for that. I didn't create the standard. It just kind of surprises me. Where the encapsulator agent is very suitable for that. Oh, that one didn't work, but that's okay. I was having some trouble with hyperlinks. So these are two videos. One's actually a distillation column of a project in China. When we do work at Texas A&M, they say, hey, what we would do for this type of a flowing fuel spray fire is we would hit it with a dual agent nozzle. We would first try to knock this out using a dry powder, you know, something like a Purple K, and then we'd come back and we would spray foam on it, which again surprises me because the dry powder, I understand, not going to put it's going to try to knock the fire out, but why are you now putting foam on top of something that's like a wall? It's a vertical surface. It's not a flat horizontal surface because the foam's just going to fall down. And if you're trying to cool, why do you want to put a blanket? It's going to trap in the heat. When they've seen some of our stuff, they go, wow, that's very interesting that it's how fast it works. The biggest issue we have is getting the standards to catch up with the agent. These are some projects that we've done in the field. This goes back and talks about an FM global study that was done back in 2006. I'm sure that if I click on that, the hyperlink doesn't work, but basically they put in their calorimeter up in Providence, Rhode Island, tested an under turbine lube oil spray fire. And what came out of that test was that the fire's temperatures reached over 1,500 degrees at the ceiling, and that was a high enough temperature that could compromise the structural integrity of the steel. So they were like, oh, that's a bad deal. So they come back and said the recommendations that are found in NFPA 850 are inadequate. They recommended a higher sprinkler density of 0.4 gallons per minute per square foot. So if you were already designed and you're at 0.3 and now you have to go to 0.4, that's a 33% increase in water. That's a major upgrade. We worked with a couple of our customers in the industry. Here's a Dominion Power. They're the third or fourth largest energy provider in the United States. And that's what they were saying is, oh, if we have to upgrade our under turbine lube oil fire protection systems, which are just plain water, and we know water is not very effective from 0.3 to 0.4, that's going to be quite expensive. And it goes, if one of the main issues is heat 30 feet above, the fire exceeds 15, why shouldn't we consider your F500 encapsulator agent, which we know reduces heat 6 to 10 times better than plain water? So that was the concept of how we got involved in this particular application. Dominion said, we're already using F500 on all of our coal plants for the Class A applications. It works. We like it. So we embarked with, this is Aegis. They're the insurance company. So that's a loss control engineer. This was a master's degree fire protection engineer, Sean Wallace. This gentleman over here, showing you how old I am, sometimers, Mark Boone. And at one time, Mark Boone was the chairperson of the Nfpa 850 Technical Committee. So they set up a series of tests to see what the F500 would do. So they said, let's test to see if this is actually a viable alternative to the larger quantities of water. So they tested 0.15, 0.2, 0.3, and 0.4 gallons per minute per square foot. Of course, me being a dumb engineer myself, I said to Mark Boone, Booney, why are you testing F500 at 0.15 and 0.2 when all of your stuff is designed at 0.3? He says, well, I really want to see what is the difference between the agent and plain water. And I don't know that I'm going to really see what I'm looking for at a higher density. So we want to test it at the lower densities to see what value the agent is actually bringing to the table. So this here is showing a 0.20 density, and it's showing plain water on one side and F500 encapsulator agent on the other. We pre-burned these up to 1100, 1200 degrees.
Mike, be careful with the microphone,
So at
please.
this point, we have thermal imaging camera, and once we reached 1100 degrees, the systems were manually put on. We ran all of the plain water tests in a row, 0.15, 0.2, 0.3, 0.4, before we added any agent, because we know that the F500, once you put it in your piping system, you might have a little residual. So we didn't want any impacts of that. So anyways, here we're seeing the plain water at 0.20. So one of the things I want to note is we got a very quick knockdown here with the encapsulator agent. That's because we're encapsulating the vapor molecules. Second, with the rapid heat reduction, we're reducing the heat in this steel below the auto ignition temperature of the fuel. So with the F500 EA, we put the fire out in 11 seconds. Sometimes when people look at this, they go, oh, well, the foam can put this out, and they're 100% right, foam can put this out. It's just that foam can't operate on an under turbine lube oil spray fire. And so that's what we're trying to do, is compare the encapsulator agent to the water for this specific application. Going to move it forward.
Mike, excuse me, but your mic, we can listen very well.
Okay. So you can see most of the fire is out, but it's still burning near the edge. It's because the water doesn't have that cooling capability. Eventually this fire goes out. Again, you see the heat in the edge is keeping that fire burning. The F500 can pull that heat out. So the conclusion was that we extinguished over 10 times faster than the plain water at the same sprinkler density. They ran the test at 0.15. The F500 put the fire out in 30 seconds, and the plain water could not put the fire out. That's why we're showing you the 0.2, because the plain water couldn't put the fire out. And then here, this is to show the 0.2 for F500 versus the 0.4, which is the FM global recommendation. Again, pre-burn up to 1100 to 1300 degrees. You've already seen this. This is 11 seconds, but we're putting it side by side with the water. Here you see it looks like they got pretty good knockdown, almost the same, even though this is half the amount of water, almost the same. But again, we see the issue here is the fire continues to burn around the side of the pan because you can't reduce the heat. You're using a very ineffective steam conversion to reduce the heat. And what do we have underneath the turbine? A lot of steel components, steel piping, hydraulic lines, tons of stuff. So here the F500 put the fire out 3 times faster than the plain water at half the density. Dominion never ran F500 at 0.3 or 0.4. They said, hell, it put the fire out at 0.2 in 11 seconds. What's it going to do at 0.3? Put it out in 8 seconds, 9 seconds? We don't care. I've seen what I want to see. We see that the agent adds a lot of value to this application. And so hence, we moved forward with Dominion and pretty much did every plant Dominion has for under turbine lube oil, transformer, fire protection. So this was also just showing the rapid reduction in temperature versus the water. I had another graph too showing the water usage. Very interesting because at a higher density of water in the time frame, they would have used 72 gallons of water versus only 8 gallons with the F500 at the lower density. So they were saying, okay, that's big because we have to contain, we have to control this water. We're going to have hydraulic oil in the water. We can't allow this to run off, and having 1/9 the amount of water is going to really be a big cost savings to us. So the key conclusions here were at 0.2, extinguished 3 times faster than the FM global recommendation of 0.4. 0.2 reduced the heat faster than the plain water at 0.4, and said since it performed so well at 0.3, they have a very high comfort level that adding F500 to the existing systems that are already designed at 0.3 would be a better form of protection than the FM global recommendation. So they and the insurance company, the AHJ, all signed off on this, and we've done multiple projects with Dominion. This was the first one. This is in Mount Storm Power Plant in West Virginia. This one had 2 3,000-gallon bladder tanks. We provided the snow on the top at no extra charge. This 3,000-gallon bladder tank is protecting Unit 1 and Unit 2 under turbine lube oil systems, and it's protecting 5 transformers. On the other side of the building, they are building another firehouse. It also has a 3,000-gallon bladder tank, and it is protecting Unit 3 under turbine, as well as 10 transformers. So all in all, 3 under turbine, lube oil fire protection, and 15 step-up transformers. Call these step-up station transformers, sometimes SST for short. They're usually right outside of the, or I say right outside of where the turbine deck is. So if they catch on fire, there's a high possibility of the fire getting inside the building, which will get to the most critical piece of equipment in the power plant, which is the turbine. This is Chesterfield plant. This is actually where we ran all the tests. They have a fire training ground here. It's where Sean set up the sprinkler systems and calibrated densities and worked with the insurance companies. And so we did that just on the other side of this plant. But here we're protecting under turbine and transformers. One of the projects I don't have shown here is Cove Point, which is a LNG compressor plant. So we're doing all the fracking, and the gas coming out of Western Pennsylvania and Ohio gets pumped down to Cove Point, which is in Lusby, Maryland, right up along the Chesapeake Bay. They compress that LNG or their gas down and put it on ships and send it to Europe. On that project, we provided close to $1.6 million of bladder tanks to protect the under turbine. In phase 2, they're going to come back and catch the transformers, which is our next application, transformers.
Hazard Control Technologies presents F500 Encapsulator Technology.
So we have a lot of transformers. They're designed for a 25, 30-year shelf life. They've been installed in the 1970s. Means their shelf life is due in, say, 2000. So the incidence of transformer fires is going up greatly, not only in the US, but all over the world. Transformer fire protection is usually designed as plain water. The philosophy is to cool the transformer, keep the fire isolated to one transformer. Don't let it get to the adjacent transformers until the fire department can show up and put the fire out. So this is what I just mentioned. Nfpa 850, it's insufficient for fire suppression. It's the containment dikes here around the transformer are undersized. In the standard, it says to contain the hydraulic oil plus 10%. And now we're going to spray plain water over the top of this transformer, overflow the containment. In fact, the Minion had one where the sprinkler system overflowed the containment, but the fire department wouldn't let them shut down the sprinkler system. So they had flammable hydraulic oil going across their parking lot towards their turbine deck. They were like, ooh, this is not the way to go. So again, we look at, okay, we have options, water, foam, encapsulator agents. Nfpa specifies sprinklers, but again, it's to control the fire, not extinguish the fire. Water's not effective, and too much water can apply a boil over. I don't think that hyperlink's going to work. Again, we've already talked about foam, not suitable for a three-dimensional fire. Have a whole presentation of a project out in California that took 6 hours to extinguish using foam from crash fire rescue trucks that came from the airport. Well, that's not a function of bad foam, because here in the United States, the FAA has a higher degree of performance for foam. You have to meet the FAA mil spec regulation, which is a higher performance standard than the UL 162. So it wasn't a matter of, geez, we're spraying foam onto a transformer and it's just bad, crappy foam. No, it was high quality foam. The problem is the foam was chest deep at the ground level, but the fire was up above, and they couldn't get the foam on the fire and keep the foam on the fire for 20 or 30 minutes until the fire dissipated. So that was the issue. So if anybody wants to see stuff on that, we have a full presentation that was provided by an engineering company addressing that. Here, yeah, we'll see. I don't think this is going to work either. No, no problem. That brought up a flyer from FDNY. They had a transformer fire. It was called Dunwoody. On that particular fire, they came out and put 1,500 pounds of purple K dry powder on, and it kind of just pissed off the fire. And then the foam chief said, hey, let's start an AFFF operation. So they started an AFFF operation, and they put AFFF on the transformer for about an hour. It didn't suppress it again. Good quality foam. It's a three-dimensional flammable liquid fire that the standard itself is saying not suitable for. Well, the foam was running down into the Bronx River, which resulted in a $5 million fine to Con Edison from the New York EPD. Of course, Con Edison was really complaining that the Bronx River was dirtying up their hydraulic oil as opposed to the other way around. And Hazmat shows up, and they've been using F500 for flammable liquid spill control since about 2003. They suggested to the foam fire suppression team, why don't you try this F500 EA? So they got out the eductor, they dialed it up at 3%, put F500 on the fire, and extinguished it in 1 minute and 30 seconds, and it was cool to the touch. Now, I've said that multiple times, and even my own staff of people and team Encapsulator Technology specialists don't believe it. And my Eastern area manager was just at a meeting in FDNY where they were talking about F500 for lithium-ion battery, and the lieutenant of the hazmat, now captain of hazmat, told the story, and he said 1 minute and 30 seconds, and it was cool to the touch. And all the fire suppression guys were over there touching it going, wow, holy shit, what kind of foam is this? And John Cassidy said it's not a foam. It's actually an encapsulator agent. It's a different type of technology. So we got invited to go meet with all the upper staff with FDNY to explain what is the difference between the foam that didn't work for that application and the encapsulator agent that did work. And so out of that, FDNY moved forward, and they now utilize Encapsulator Agent on all of their 3D Class B fire applications. They use it for lithium-ion battery. They're using it for some Class D. They're just trialing it for D, but they haven't given up their foam. They still have foam applications, and I understand that. So I think that's pretty smart. But what happened was, because of the performance, they came back and said, since this agent's so effective, let's test it to see if we can actually spray this agent onto an energized transformer, or at least onto a de-energized transformer in an energized environment. Because transformers are at power plants, and while one of them may be on fire and de-energized, all the equipment around you is still energized. So we embarked with FDNY and Con Edison to do some leakage current F500EA conductivity studies. These are just some pictures from the fire ground. Quick overview, they tested AFFF, ARAFFF, and F500. The desired current to the nozzle had to be less than 0.9 microamps or milliamps. Initial testing was conducted at 50,000 volts. The conclusion was the AFFF and the ARAFFF failed. Both exceeded this limit. Because I remember getting a call from a guy named Mr. Anthony Natali. He asked, has F500 encapsulator agent ever had any leakage current testing done? And I said, oh, yes. And he said, what? It has? I said, yes. We did some testing with Penelac at Conshohocken, Pennsylvania on a 16,000 kilovolt screen. And here's what we know. If we take a plain water nozzle and we have a straight bore, a straight stream, you have leakage current can come back to the nozzle, it will kill you. If you open that nozzle to a broken fog pattern where you have individual droplets and no pathway back to the nozzle, it was safe. When you put F500 into the stream at 3%, if you spray it on with the smooth bore fashion, the current will come back to the nozzle and it will kill you. If you open it up to a broken fog pattern where you have droplets and don't have a single pathway back, it was safe. So my friend, Mr. Anthony Natali, it's a function of the spray pattern and not the agent. And to that, this is what he said. Au contraire, my friend, be careful what the F you say. And I was like, oh, enlighten me. What do you mean? He goes, well, we've tried this with AFFF and RFFF foam, and regardless of the spray pattern, because you have bubbles, you have bubble-to-bubble interaction, you always have a pathway back to the nozzle. So they said, okay, let us run some tests. So they tested it at, this isn't going to work, is it? Yeah, the video, I'm not going to be able to show the video here, but they tested F500 up to 240,000 volts through 3 different appliances and found it to be safe. And so FDNY has created an SOG. We have that SOG or standard operating guideline that's available, but with the 30-degree fog nozzle, 30-degree fog nozzle. Hang on a minute. Sorry. You could have a standoff distance of 25 feet and not have a current leakage back to the nozzle that exceeds the 0.09. And then with the deck gun, you had to stand back 125 feet, and with the multiversal 5,000 gallon per meter was 100 feet. And so they moved forward, and we ended up putting together a presentation for FDNY, went up and did training to all their firefighters. Since that Dunwoody fire, they've had at least 15 different transformer fires, and none of them have taken more than 5 minutes to extinguish with F500 encapsulator agent. So they're very happy with the use of the agent. Now they're looking at parlaying that into lithium-ion battery applications. This is a comparison of 2 fires, and I have a video for this, but I'm not sure I'm going to be able to play that video either. Alabama Power plant Gorgas has an actual fixed system in place. They had a transformer fire. They recorded that transformer fire on the security video. It took 3 minutes and 10 seconds to extinguish. There was no human interaction at all. They called the local emergency responders as soon as the alarms went off that they had a transformer fire. The F500 put the fire out, and they turned the emergency responders around before they ever arrived at the first gate. So they used a total of 100 gallons of solution and only 3 gallons of F500. They had a minimum cleanup cost. When I talked with the power plant, they said, oh, we just took apart our sprinkler system. The old transformer was garbage. We took it out. We had a little bit of charring in the rocks. We took the rocks out. We put new rocks in. And we had another transformer at another plant. We brought it over, rehooked it up, put the fire protection on, filled the F500 tank, and we were back in business in 4 days. They had another transformer fire at a Georgia power plant that's all owned by the Southern Company. They had plain water. It didn't put the fire out. The firefighters showed up, sprayed foam on it for 4 hours, finally put it out, had 2 injuries, and ended up with the $2 million environmental cleanup bill. And I don't know if you know where this is going. The $2 million environmental cleanup bill. The cleanup itself took 6 weeks. They were out of service on the transformer for 8. They said, this is a no-brainer. On one side of the equation, we put the fire out. Everything's contained. No human interaction. No environmental cleanup bill. On the other side, we're out of service for 8 weeks. So they've moved forward with putting F500 on all of their fixed systems. This is a comparison between the Alabama Power and Duke. Duke was a 6-hour extinguishment with 2 fire departments, 400 gallons of AFFF, 50,000 gallons of water. So just the agent cost at 20 bucks a gallon was 8,000. I can imagine what their cleanup costs were. So for transformer fire protection, again, the code's really designed to just control the fire with plain water. The F500, adding it is suppressing the fires. These are just also showing some portable delivery systems. This is something we promote with the power industry, because if you have a transformer and you have a fixed system and your transformer explodes, and it takes out some of the sprinkler system, you may have to have a manual attack. So some of our customers are using trailers like this that are designed with monitors, say 250 up to 500 gallons per minute. Others are using the F500 turbo cannon. Yeah, that's what I was expecting. So here's a transformer fire at Springerville. They used this unit. They were able to extinguish that in about 45 seconds. So they don't have a fixed system, but they were able to do it. So, you know, the concentrate control systems are for transformer turbines, critical coal handling components. They can be used on lithium-ion battery in the petrochemical industry. So the transformers are not just at power plants, steel mills, refineries, anyone that automotive places, anyone who has large power demands, big industrial, pulp and paper mills, paper processing facilities, all have these type of applications. So, you know, what we push and promote is for the concentrate control systems is mainly the 3-dimensional Class B fires. And we promote a manual backup type system as well as training. So it's a unique category of agent. It encapsulates the fuel molecules. This says hydrocarbons, but it's actually carbon materials, unburnt carbons, the hydrocarbons and polar solvents. Unmatched heat reduction inhibits smoke and cancer-causing agents. Does very good 2D and 3D fire protection capabilities, and you can do a direct application in an environment up to 500,000 volts. And that again is in the New York's SOG. By the way, after seeing how the agent worked, this gentleman, Anthony Natali, who's the head of emergency response for Con Edison, joined the NFPA 18A technical committee, and he has brought some of that testing, and that's been folded into the NFPA 18A testing, so that you would be able to now, once UL is geared up to do it, because currently they're not geared up to do it, you would be able to go and get your agent listed for electrical devices with certain standoff distances with the agent. Currently, the only Class C listing criteria available in the world is UL 711 for a fire extinguisher. And we're certainly not going to go on out to a transformer fire with 20,000 fire extinguishers. So, you know, it's one thing I'll say about HCT is we've been leaders in the industry, not necessarily to follow a path, but to go somewhere else, blaze a new trail, and leave a pathway behind us. So we've innovative systems that include sprinkler systems, deluge, the VEEP system. We do provide loose equipment, quick attack mobile units, 25, 50, 75, 100 liters, portable carts. We do supply both the CAS system, which is a compressed air suppression system. We use that with the F500 because you don't have to air and train any F500 any air into the F500 because we're not trying to create bubbles. We're creating spherical micelles. So we'll use the system, but without any air entrainment into the hose stream. And then we do supply CAF systems because we have Class A foam that's also fluorine free that will push through compressed air foam systems. We provide mobile response trailers, piercing rods, and then our concentrate control supply systems. We do bladder tank systems, water-driven proportioners, but we do have one balanced pressure pump system that is installed. In fact, that system was installed by Williams Fire and Hazard Control. It's outside of Memphis, Tennessee. Used their ratio controllers and pump proportioning systems. It was actually installed by International Fire Protection, but it's Williams Fire and Hazard Control equipment working in conjunction with the F500 on that rubber tire warehouse storage project. HCT does consulting and training all over the world. Some of our consulting has to do with coal handling, dust protection, dust hazard analysis, emergency response planning, emergency response preparedness trainings, deal with combustible dust, bulk storage, hazard awareness, coal handling, emergency response training for different applications that involve Encapsulator Technology, for example, dust collectors, deep-seated slow burning coal silo fires, lithium-ion battery. So we have a series of people who can do training. So we were choosing to be a full-scope Encapsulator Technology Solution provider. Boy, that's a whole mouthful. Encapsulator Technology Solution provider. So the question is, how can we help you encapsulate your world? Any questions that Mr. Anand can answer?
That's good.